Hi everyone. In this lecture, I'm gonna talk about optimization. So, introduction to Riemannian optimization, an introduction to optimization on Riemannian matrix manifolds. So, what is that? First off, let me talk about Riemannian manifold. Vector space. What is a vector space? A vector space, also called a linear space, is a set whose elements, often called vectors, can be added together and multiplied or scaled by numbers called scalars. So in simple words, we can scale the vectors by some scalars, and then we can add them together. So we can have addition of linear combination of vectors in this space. This is called a vector space. Of course, a vector space contains the origin. Why? Because a vector minus itself is the zero vector, which is the origin, and it needs to be in this space. Okay. Euclidean space is a vector space, but with the Euclidean distance metric defined over it. It means that when you have 2 points in this vector space, every point can be represented as a vector. Why? Because every point can be seen as a vector connecting the origin to that point. When you then you can say, okay, I can calculate the Euclidean distance between 2 points or equivalently between 2 vectors, right? And the Euclidean distance metric between 2 points is the length of the line connecting these 2 points together. So the length of this line is called the Euclidean distance, and this Euclidean distance can be calculated by L2 norm of that, by the L2 norm of the vector connecting one of the points to the other one. Smooth manifold. In simple words, it is a differentiable curvy hypersurface. So what do I mean by hypersurface? So in one dimension, 1D, one dimension, it is a line. In 2D, it is like a plane in R2, right? In 3D, it can be a plane like this, a linear plane, or it can be nonlinear, a nonlinear surface such as this, right? In 4D, we'll have we can't visualize it and we need to imagine it. So surface is not necessarily linear. You can see it as a plane or a hyperplane, which is not necessarily linear. A hyperplane is a special case of a hypersurface, right? Okay. Then, generally speaking, a curvy hypersurface, we can see it as a smooth manifold, and it's differentiable where you can. It means that it is a smooth, and you can take derivative in all points in that manifold. Okay. In mathematical definition, it needs the concepts of topological space, chart, and homeomorphism, which we are gonna talk about in this lecture. Riemannian manifold, denoted by M standing for manifold. In simple words, it is a real, because the manifold can be complex too. This is a real manifold. Smooth manifold, it means it is differentiable, and it has a Riemannian distance metric on it. What is that? It's a distance on the curvy hypersurface. So when you have a curvy hypersurface, you have 2 points. What is the shortest line, curvy line, connecting them on the manifold? So it's not a straight line anymore necessarily. It can be like this, a curvy line like this. Then the length of this curved line connecting these 2 points on the manifold will be the Riemannian distance metric between these 2 points. So when we can calculate the distance metric on the smooth manifold, then that's a Riemannian manifold. This is in simple words. In mathematical definition, it is a real smooth real manifold. First off, it's real. Second off, it's smooth. Equipped with is a terminology used a lot in differential geometry. It means that it has a positive definite inner product. So you can calculate the inner product of the vectors in the tangent space of the manifold. We are going to talk about these in a few slides. So you can calculate the inner product in that manifold on the tangent space at each point. And this inner product is called the metric of the manifold. So we are going to explain the details of the mathematical details of these in a few slides soon. Okay. Euclidean optimization. So I have had a course on optimization techniques. You can see it in my YouTube channel. In that course, whatever I said was Euclidean optimization. Usually the regular optimization that we have heard of is Euclidean optimization, where we are optimizing the Euclidean space. For example, the cost function is a function from the Euclidean space to a scalar, like this. When assume that the dimensionality of the optimization variable is d, it is d-dimensional. It goes from rd to r, a scalar. It might, by the way, the input might be a matrix, not necessarily a vector, or the output is not necessarily needs not necessarily to be a scalar. It can be vector or whatever, but it goes from Euclidean space to another Euclidean space. So it's a mapping from x to f of x. The optimization problem can be seen as this: minimize the function f of x with respect to x, which is in Rd, right? Or equivalently, we can write this equation 1 as this: minimize f of x with respect to x subject to x belonging to Rd. Rd is the d-dimensional Euclidean space, right? It means that x is a d-dimensional vector in the Euclidean space. So I have brought these as a constraint. Usually in Euclidean optimization, this is a default constraint. So when we have only this constraint, we can consider this optimization as an unconstrained optimization problem. So if the optimization problem is constrained, we actually have inequality and equality constraints. Well, then we have a feasibility set defined by the intersection of the constraints, and that will have this: minimize f of x with respect to x subject to x belonging to the feasibility set. Okay. Now, so far, whatever I have said in my course, I covered optimization methods in the Euclidean space. The Euclidean optimization methods can be now slightly revised to have optimization on possibly curvy Riemannian manifolds. So rather than having optimization in the Euclidean space, we can have optimization on the Riemannian manifolds, which are possibly curvy, because Euclidean space is flat. And note that Euclidean space is a special case of Riemannian manifold, which is flat, right? So we can generalize the Euclidean spaces to Euclidean optimization algorithms to Riemannian optimization algorithms. In Riemannian optimization, you can take a look at references 1 and 2, which are the books in this field. What do? It optimizes a cost function while the variable lies on a Riemannian manifold M. So the variable is in the manifold, is on the manifold. It belongs to the manifold. Rather than belonging to the Euclidean space, it belongs to the manifold. The optimization variable in the Riemannian optimization is usually a matrix rather than a vector. It's usually a matrix. Therefore, Riemannian optimization is also called optimization on matrix manifolds. It's also called optimization on matrix manifolds. Okay. So here we have this. We say the function in Riemannian optimization is a mapping from the manifold to the real number, to this scalar. So the domain of the X is a manifold rather than the Euclidean space. And as it is usually a matrix, it doesn't need to be a matrix. The manifold might be a manifold of vectors, but as usually it is a matrix, I have denoted by capital bold. But in the Euclidean optimization, I denoted by the small case bold, showing it is a vector. This is a usually matrix, x to f of x. Okay, now I minimize the function f of x with respect to x belonging to the manifold M, right? Or equivalently, I can restate it as this. Minimize f of x with respect to x subject to x belonging to the M. So I can see it as a constraint. Compare this equation 5 with equation 3, or sorry, with equation 2. Compare these with this. And now you will see that Euclidean optimization is a special case of Riemannian optimization where manifold M is the Euclidean space, right? Okay. Now, there is a good technique. Sometimes we have a Euclidean optimization problem. We can convert it to a Riemannian optimization problem. How? Some constraints are the constraints. Those constraints are actually some manifolds, some well-known manifolds. For example, if my constraint is like this, minimize, let f of x be x transpose a x, where a is a positive semi-definite matrix, known matrix, with respect to x subject to x transpose x equals I. I is identity matrix. Something like that. We have this form optimization problem in many, especially eigenvalue problems, such as in machine learning, we see it in principal component analysis. Similarly, we have it in Fisher discriminant analysis. So we have this form of optimization a lot. In theoretical physics, we also have this kind of optimization. So this constraint, x transpose x equals I, means that the matrix X, I want it to be an orthogonal matrix. It means that I want its columns to be orthonormal, meaning that the inner product of the columns, different columns, is 0, but the length of the columns is 1. So this actually is a well-known manifold. Manifold of orthogonal matrices is called Stiefel manifold. I think we will see it in a few slides. Stiefel manifold. And therefore, we can say, rewrite this as restated as this: minimize trace of x transpose a x with respect to x subject to x belong to the manifold of Stiefel. So in this technique, I converted this Euclidean optimization problem to a Riemannian optimization problem. If the constraint, for example, says that I want x to be consider another constraint. X be positive definite matrix. It means that its eigenvalues, I want its eigenvalues to be positive, neither negative nor 0. Then this is actually SPD manifold. SPD manifold is symmetric positive definite manifold. So I can write it, minimize trace of x transpose a x subject to x belongs to the SPD manifold. Another thing that is that if I want to find projection onto a subspace, so I'm learning a projection matrix, a linear projection matrix. It is used a lot in various machine learning algorithms for linear projection, such as in PCA, principal component analysis. Then, in these cases, I can have Grassmannian manifold. Grassmannian manifold is a manifold for projection onto the subspace. Okay, and then you'll see that many machine learning algorithms are formulating the optimization problem as a Grassmannian manifold. So especially it has been used a lot in action recognition. So you can see that I can convert many of the Euclidean optimization problems to Grassmannian optimization problems. Okay, sorry, to Riemannian optimization problems. Many of them can be converted to Riemannian optimization problems. Some examples are Stiefel, Grassmannian, SPD manifold. We are going to review them briefly in a few slides. Okay. So this is a good, again, let's read this good technique that I explained. If the optimization problem is constrained, we may define the constraint as a matrix manifold of that constraint, such as a Stiefel manifold, which is the manifold of orthogonal matrices, manifold for x transpose x equals I, and use equation 5 to solve it. Okay. Now, again, let's compare Euclidean optimization and Riemannian optimization. In Euclidean optimization, F is a mapping from RD to R, a map from X to F of X, and we are minimizing F of X with respect to X subject to X belongs to the RD, D-dimensional Euclidean space. So for example, if D is two-dimensional, then we can show F as one of the dimensions. This is the cost value. I want to minimize it. I can look at it from above. It will be like this. These are at each curvy line, the function value is the same. So I can say F is a mapping from this two-dimensional or D-dimensional space to a scalar R. In Riemannian optimization, likewise, we have a map, but from manifold M, Riemannian manifold M to scalar, or X to F of X. We can write it as minimize F of X with respect to X, subject to X belongs to the manifold M. So we can show it like this. This is a curvy manifold M. The function value, I can show it in this way. So for example, here, it's like similar to a quadratic function. Here it's minimum and it's increasing on the manifold. Something like that. So you can see this F as a map from this manifold to a real number, to a scalar. Right? Compare these two and you will understand what we are talking about. Okay. What do we do in Riemannian optimization? So in Euclidean optimization, assume we're looking from above. I'm starting from some point, some initial point in the D-dimensional space, and then I'm iteratively, I'm going toward the solution. So for example, like in gradient descent, in first order methods, I'm gradually moving toward the solution, right? Also, Riemannian optimization, we start from some point, initial random point on the manifold, and I move on the manifold toward the solution, and what is the solution? One of the points in the on the manifold, where the cost function is minimized at that point, right? This is Riemannian. Okay. Now let's talk about topology and smooth manifold concepts. These are some concepts which you can find in differential geometry and algebraic topology. Okay. Topology and topological space. Let's define them. You can take a look at references 3 and 4. Let X be a set, be some set. A topology on X is a collection T. By the way, collection, you can see it as set. In my opinion, I might be wrong, but as far as I know, collection and set can be used interchangeably in pure mathematics, but there might be a slight difference between them. But I myself look at collection as a set. So it's like a set or collection T. So a topology on X is a collection T of subsets X okay, called open sets. Why do I call it open set? Open set is a set where it doesn't belong, it doesn't has its boundary, but closed set has its boundary too. So open set is only its interior, excluding the boundary, but closed set is a union of the interior and the boundary. Okay, so open sets, we are talking in topology, we are usually talking about open sets. So called open sets satisfying these three things. So first off, these collection T, the empty set and the whole set X belong to this collection T. Also, if there are K open sets in this collection T, so this T contains the open sets, some open sets like these. Okay, if K open sets belong to the collection T, then their intersections also belongs to this collection T. In other words, finite intersections, K is finite, right? Finite intersections of open sets are also open. Belonging to T means that they are open, right? An example is that, consider these. Assume I want to calculate the intersection of U1, U2, and U4. What is their intersection? It's here. This is also an open set, so it is in T. If U alpha belongs to T, where for all alpha in A. What is A? It's the index set of topology. It means that the index set means that the indices of these open sets which are in the collection T. For example, if collection T has 4 open sets, then A is the set of 1, 2, 3, 4. So it's the set of indices. So for all indices, it simply means for all indices of the open sets. For all U1, U2, U3, U4, or, and etc. in the collection T, their union is also in the collection T. In other words, arbitrary unions of open sets are also open. An example is this: U1, U2, U4. Consider this. What is their union? It's this, right? This is also an open set. So it belongs to T. X was the set, T was the collection of the open sets. Okay? And this pair of X and T, and what was T, by the way? T is a topology on X, right? T is a topology on X. We defined it here, which satisfies has these characteristics. But the pair X and T is a topological space associated with a topology T. And the topology T is a topology on the set X. The pair X and T is a topological space. Okay? Now, another important concept is Hausdorff space. You can take a look at references 3 and 4. A topological space, X and T, is Hausdorff if and only if, so it's two-sided, if and only if, for 2 points, x1 and x2 in X, this X is the set X, where x1 and x2 don't equal to each other, so they are disjoint. They're 2 different points. We have this. What is this? It means that there exists 2 open sets U and V such that x1 belongs to U, x2 belongs to V, and U and V, their intersection is empty. In simple words, what is this? I have visualized it here. For example, for every 2 points, x1 and x2 in the X, you can find U and V, 2 U and V open sets, where U contains X, so X belongs to U, and V contains x2, so U contains x1, V contains x2, and U and V, their intersection is empty. They don't have any intersection. In simple words, means that the points are separable. So here, The points of a Hausdorff topological space are separable and distinguishable because you can find their neighborhoods, some neighborhoods of them, or some open sets containing them, which are with some gap between them. They don't have any intersection. So it means that they are separable and distinguishable, right? This is Hausdorff space. Okay. Now, homeomorphism and diffeomorphism. Homeomorphism. These are homeomorphism is a very important concept in algebraic topology. It is a transformation. It is a transformation from one topology to another topology without tearing up the topology. So you don't tear up the topology. You can deform it. You can deform the topology, but you don't tear it up. It is studied in algebraic topology. So the two topologies before and after homeomorphism transformation are called homeomorphic to each other. And its symbol is this. It's denoted by this. What does it mean? It means that in algebraic topology, you can see it somewhat like equivalence, right? It means that in algebraic topology, as long as you don't tear up the topology that you have, you can deform it. Deformation doesn't change the topology. So the topology before and after deformation without tearing up remains the same. They are equivalent. They are homeomorphic. An example, a famous example is cup and a donut or torus. Torus in algebraic topology means that something like some manifold like this or topology like this, which has some holes. So we can have a torus with 2 holes like this, or a torus with 3 holes like this. A torus with 1 hole is like a donut. That's why it's also called donut. So a cup and a donut or a torus with 1 hole are homeomorphic. Why? Let's see. So here I can deform cup to become a donut without tearing it up. What do I mean by tearing up? It means that I make them. It means several things. One thing it means that tearing up might mean that I completely tear it up to become 2 disjoint topologies, or I forcefully add some hole in it, right? It doesn't have any hole. For example, it's like a ball, but I tear it up, so I add a hole in the middle of the ball and it becomes like a donut. So I know that a ball and a donut are not homeomorphic to each other. Why? Because I can't deform a ball to become a donut without making a hole in the middle of it and tearing it up. Okay. Therefore, however, cup and donut are homeomorphic. Why? Or equivalent in terms of algebraic topology. Because assume this is the cup. Here, it's not a hole. I can fill it up. I can increase this height. I can deform this and increase this up height without any tearing up. So I can fill the cup completely, and then I can shrink this part to become like this. I'm just deforming it. I'm not tearing it up. And then I can shrink this completely, so it becomes like this. It becomes like a donut. So gradually you can see I can make this to this, and this hole in the donut or the torus is the hole for handle of the cup. Right. Okay. Now let's talk about diffeomorphism. Diffeomorphism is a homeomorphism transformation which is smooth and differentiable. So as long as the homeomorphism it is a smooth, so the topology before and after homeomorphism is smooth and differentiable, so you can take the derivative on every point in the topology, then it's diffeomorphism. For example, consider this. This is not a smooth in this point, right? It has a corner. A cup and this are actually homeomorphic because you can convert this to this. However, they are not diffeomorphic. So they are not converted to each other by diffeomorphism because this is not differentiable anymore, smooth anymore, right? Okay. Now topological manifold. Reference 3. A topological space X and T is a topological manifold of dimension D where D is a positive or where D is a non-negative integer, 0, 1, 2, 3, 4, whatever. This topological manifold of dimension D is also called topological D manifold. So I think you have heard of this a lot in mathematics. 3 manifold or 3 sphere. If you take a look at papers, you see a lot of these 3 sphere, 3 manifold. It means that this is a topological manifold of dimension 3, or this is a topological sphere manifold with dimension 3. Okay. So what do they mean? A topological D manifold. It means that this topological space is Hausdorff. It has also countable bases, so we can count its spaces. And it is locally homeomorphic to a D-dimensional Euclidean space RD. This is an important thing. I think the third one is very important and needs discussion. What does it mean? First off, it means it is locally. What does it mean? Let's see some examples. So I said, for example, 3 manifold and 3 sphere. Okay, some examples. This curve. This is locally, if you take a look at it locally, it is one-dimensional, right? Locally, it is like a line. So locally, it is a one manifold. Although you can embed it or show it in 2D, but locally it is 1D, one manifold. Consider a plane or a surface shown or embedded in 3D, but locally, if you take a look at it, locally, like I'm trying to look at this part, locally it's like this. It is similar to a square or something like R2. So locally it is two-dimensional, so it is two manifold, although we are showing or embedding it in 3D. Okay. Another example, a ball which contains inside of it, shown in 3D, similar to Earth. What is it? Let's take a look at it locally. A local part of it is like a cube. If you take a part of the Earth, take some mud from the ground, that's a part of the Earth. That's actually a 3D thing, a 3D object, right? Or 3D, you can see it as a 3D ball or 3D cube, whatever. That's because 3D cube and 3D ball, they're homeomorphic to each other. So I don't care about the shape, about the deformation. That's why I don't care in algebraic topology. So locally it is 3D. So actually the Earth or this ball is 3 manifold, although it is embedded in 3D. So you can see this is a 2 manifold embedded in 3D. This is a 3 manifold embedded in 3D. Now compare this with this. In 3D, Rather than a ball, let it be a sphere. What is the difference of ball and sphere in mathematics? So, or in algebraic topology, ball contains the interior, its boundary and the interior. But a sphere is only boundary. It doesn't have its interior. That's why for norms we say unit balls. We don't call them unit spheres because we also consider their interior. Okay. Here, what is it locally? So it's like the surface of the earth. We don't have the inside of the earth anymore. It's like the surface of the egg, something like that. Then locally, it is like this. I can deform it to be like this, and it is R2 actually. It's homeomorphic to Euclidean, two-dimensional Euclidean space. So locally, it is 2D. It means it is a two-manifold. Although it's embedded in 3D. So see, this is three-manifold embedded in 3D. This is two-manifold embedded in 3D. Now I think you can see what I mean. And but for seeing how locally what I mean, you need to zoom. You need to zoom and become like an ant and put yourself like an ant on the manifold and see how, because an ant can't see the global structure of the manifold. So you need to go and see it locally. You need to zoom like an ant to become very small. The ant on this curve only sees a line. The ant on this curve, on this, sees this surface, R2 is surface. The ant in this sees actually a cube, and on this sees a surface, right? That's why this is called, this is a two-manifold sphere. This is also written as S2. This is a three-manifold of balls. This is called as B3. B3, but S2. So this is important. When you say, you see in the papers or literature S3, it doesn't mean a three-dimensional sphere where you can visualize it. No, it's actually like a four. It's you should imagine. Yes, for yes, locally it is 3D, but it is embedded in four-dimensional. So I can't visualize it anymore. You need to imagine it. You have a four-dimensional space, and this sphere is locally 3D. You shouldn't confuse it as being embedded in 3D, a sphere in 3D. No, it is a locally 3D sphere embedded in 4D. However, B3, you can visualize it easily. It is a ball in 3D. B2 is a ball in 2D. It's like a circle, but it has interior. S2 is just a circle without, no, this is S1. This is S1. This is S2. S1 is a circle without its interior because locally it's like a line. So that's an important thing in algebraic topology, which you should note. And that's related to this. So when you have a manifold, a topological manifold of dimension D, it means that locally it is D-dimensional. It might be embedded in D+1 Euclidean space. So you can, you should note the difference here. Okay, now chart. You can see the reference 3. Consider a topological manifold M, X, and T, because do you remember what was topological? So topological manifold, we had a topological space X and T. Then from that, we defined a topological manifold, which itself was a topological space satisfying these. So now consider topological manifold X and T, we denote it by M. It is locally homeomorphic to RD, locally D-dimensional, meaning that all X in the X, for all of them, there exists an open set U containing X and a homeomorphism phi from U to phi of U where phi of u is an open subset of Rd. By this visualization, I think you will understand what I have said here. So simply it means that consider this manifold M. So for example, in this visualization, this manifold is locally 2D. D is 2 here, okay? Then consider a point X in this manifold. And then I can have an open set U on this manifold containing X here. U containing X. And then I can have a map phi from this open set U to phi of U here. And this phi of U is homeomorphic to Rd. Here it is R2. I think it's obvious, right? Because locally it is 2D. So you can imagine this to be in a R2 Euclidean space, right? Although this is curvy, but you can deform it to become flat in the two-dimensional space. So this is phi U. You can do the same for V, another open set containing X, and you will have, by a mapping psi, another mapping, you will have psi V. And this intersection also has been shown here, right? Phi of U intersection V or psi of U intersection V. And interestingly, you can go back and forth between these two. How? For going from here to this, I can say, what do? So I want to go from this to this, from this phi of U to psi of V. I should say first apply phi inverse. So go to this manifold again. From here, go to manifold, and then apply psi on it to come here. So for going from this to this, I need to go first go to the manifold by phi inverse, and then by psi, I come back here. I can also go from psi of y to phi of u. How? Psi of v to phi of u. How? I need to take the psi inverse first to go to the manifold, and then take the phi of that to come here. So I can go back and forth between these two. And what is C infinite? So C1 means it's a smooth for the first order derivative. C2 means it's a smooth for first and second order derivatives. And so on. C infinite means that it is smooth for all orders of derivatives. Also here, F is the mapping of do you remember the cost function from this manifold to a scalar? Okay. And now let's go back to what we were saying. I think now you understand. There exists an open set U containing X and the homeomorphism phi from U to phi of U. Why is it a homeomorphism? Because this is curvy on the manifold, but here it is flat. So you are deforming it to become a flat thing. Where phi of U is an open subset of Rd. Such mapping is denoted by this. And this is the notation of homeomorphism, right? And the tuple U and phi, U was this, and this is the phi mapping. The tuple of U phi, or the pair U and phi, is called coordinate chart, or chart in short, for manifold M. So this phi and this mapping, this U and this mapping phi is one chart. Another chart is this V and this mapping psi, right? So we have many charts, not just one. So this is a chart, this is a chart, and we can go back and forth between the charts, as I explained. Okay. Smooth atlas, reference 5. A smooth atlas A for a topological D manifold M. So a manifold which is locally D-dimensional. It's a collection of charts, U alpha, phi alpha for M, manifold M. So collection or set of charts. Do you remember I said we have many charts? Now consider a collection of charts. U alpha and it means that U1, phi 1, U2, phi 2. So here, for example, I denoted phi 2 by psi. Doesn't matter. The naming doesn't matter. So U1, phi 1, U2, phi 2, U3, phi 3. Where they cover M, it means that their union covers the whole manifold. Something like this. Consider all of these open sets on the manifold. Their union becomes the whole manifold, right? And any two charts in this collection are smoothly compatible. Exactly what I said. You can go back and forth between these charts smoothly. So I can go from this to the manifold and come back here. And it's a smooth, C infinite, right? Note that two charts U and U phi and V and psi are smoothly compatible if the mapping this is a diffeomorphism. It's a homeomorphism, which is also differentiable, right? It's and it's smooth. Okay. So when we have these collections of charts, so these are the open sets of the charts, and they also each of which has a mapping, a homeomorphism. This collection of charts is called a smooth atlas. I think by its name, you will understand it easily. Atlas means that it's covering the whole thing, right? Okay. Definition. Maximal atlas, reference 5. A smooth atlas A for a topological D-manifold M, locally D-dimensional, is maximal if it is not contained in any other smooth atlas for M. Okay, this is a maximal atlas. Now, a smooth manifold and Riemannian manifold. Now, so far we talked about what? We started from topology and topological space. We talked about Hausdorff space and homeomorphism and these, and then we defined topological manifold, which is a topological space with some characteristics, right? So far we had defined topological manifold. Now let's define a smooth manifold. A smooth manifold M of dimension D, which means locally D-dimensional, also called a smooth D-manifold, is actually a topological D-manifold, but has some other things too, together with a choice of maximal smooth atlas A on M. So smooth manifold is a topological manifold, but with some maximal smooth atlas. Okay, now we have defined topological manifold, then a smooth manifold. Now let's define Riemannian manifold. Riemannian manifold is a step ahead. Riemannian manifold M is actually a smooth manifold, but with some other characteristics. What is that? It's a smooth manifold which has a metric or inner product G. First off, don't confuse this metric with distance metric. Distance metric is something else, satisfying having 3 or 4 characteristics, including triangle inequality, right? Like what we have in norms. So that's another thing. That's distance. Metric here in Riemannian manifold means inner product on the manifold. So when you have two vectors on the manifold, you can calculate their inner product, similar like this. So you have two vectors on the manifold. Locally, these two vectors are in the tangent space at this point. I will define the tangent space in a few slides. So you can calculate the inner product of these two or dot product of these two vectors, and that's defined by the metric on the manifold. So Riemannian manifold is a smooth manifold with some metric, some inner product. And interestingly, by the metric, you can when you have the metric, you can calculate almost everything on the manifold. Inner product on the manifold. You can calculate the distance on the manifold. So note that the distance is not Euclidean distance anymore. It's Riemannian distance. So it's the length of the curvy line connecting the 2 points on the manifold. you can calculate the geodesic, which is the shortest curved line on the manifold. So because you can come from this point to this point along the manifold in this way too. Assume the manifold its curvature is like this. However, there might be another path on the manifold from this to this, which is this is shorter than this. So you take this as a geodesic. And the Riemannian distance is the length of the geodesic between 2 points, right? Curvature. So you can calculate the curvature on every point on the manifold. Assume, for example, consider a one-dimensional manifold like this. Let me have another figure. This point has a positive curvature. This point has a positive curvature. This is negative curvature, for example. This is negative curvature, okay? And this point has higher curvature than this because it is sharper, kind of. It has higher curvature than this. And so I think by this you understand what I mean by curvature. Now extend this to be locally 2D or locally 3D, whatever manifold. So we have some curvature, and this is curvature. Shows how up and down the manifold goes. So you can calculate all of these using metric. And this metric, by the way, can be seen as a matrix of it, and it has some formula. For different manifolds, its formula is different. Its expression is different. So you can at every point you can plug the point in the metric, and it gives you the metric at that point. So you can calculate the metric at every point on the manifold. Okay. Riemannian manifold constants. Before saying that, I want to mention one thing which is about interesting in topological manifold. Yes. So one thing which I wanted to say is that there was a conjecture, Poincare conjecture. Poincare conjecture in algebraic topology and differential geometry. What was Poincare conjecture? It said that when you have what in d-dimensional, when you have a d-dimensional, locally d-dimensional topology, which doesn't have any hole in it, okay, you can deform it using homeomorphism to become an SD manifold. It means that to become a locally d-dimensional sphere. That's an interesting thing. So some examples are like this. For example, let me share a screen with another thing. Like this. For example, locally 1D, consider this shape. I'm talking about this shape. It is locally 1D. I can deform it to become like S1. Like, so this is homeomorphic to S1. Locally 2D, I can have this form. This is locally 2D. I can deform it without making many tearing up or holes. It's homeomorphic to S2. So it's locally two-dimensional sphere. I can have the same in S3, S4, and all dimensions. So this was the conjecture of Poincare. Poincare was a scientist in mathematics. Okay, and then so it was proved over, I think, a century by different mathematicians for different dimensionalities. First off, I think it was proved for dimensions more than 4 or 5, something like that. And then someone proves for dimension 2 and 1. I think 1 was obvious. But for lower dimensions, I think it's intuitive and very obvious. but in higher dimensions, you need to imagine it, right? And in there, it was solved for all dimensions except in locally 3D. So in S3, like I have written it here, S3. So if you have a locally 3D manifold, you can't visualize it. You need to imagine it because it can be embedded in 4-dimensional Euclidean space, R4. So it is locally 3D. You can deform it by a homeomorphism mapping to become a S3 a manifold or a 3-dimensional, locally 3-dimensional sphere. You need to imagine it. You can't visualize it. Okay, so it's locally 3D, and then the scientists couldn't prove that. Apparently, as far as I have researched, apparently in 4 dimensions, algebraic topology has very weird characteristics. It has been seen, observed in other things in algebraic topology too. Apparently in 4 dimensions, there are very interesting characteristics. Okay, that's why maybe it had become very hard in 4 because S3 can be embedded in R4, right? 4 dimensions. Then no one could solve that, and after a while, so someone named Hamilton proposed Ricci flow. What is Ricci flow? So he named it after Ricci, who was a scientist before him. But Ricci flow is saying that when you have a curvature, go to the other side of the curvature, like in your optimization, as you go to the other direction of the gradient. So you go to the minus gradient, you go to the other side of the curvature. By doing this, you will see that you reduce your topology. For example, like this, something like this. Consider you have this topology. It means that the curvature says that it's in this direction, but it says that go to the other side of the curvature. So go in this direction. Move this point toward inside. And this curvature, its curvature is in this side. Don't go to this. Go to the other side. So move this to this. And also move this toward inside. So wherever we have a positive curvature, we go inside. Wherever we have a negative curvature, we go outside. So gradually, you will see it becomes like a sphere. Also, it shrinks because after a while, it becomes a smaller until it becomes like a dot and it disappears, right? So this is the procedure of Ricci flow. What we are doing here is called Ricci flow, written as this, Ricci flow. And he proposed that, Hamilton, and then a scientist named Grigory Perelman, who was a Russian scientist, because Russia has a lot of good mathematicians. He took this Ricci flow and actually proved this Poincare conjecture for S3, for locally 3D manifolds. And how did he do that? He said, okay, I will. So Hamilton also went up to this point that, okay, using the Ricci flow, I can say that I have some locally 3D topology or manifold. I do the Ricci flow, so it gradually becomes like a sphere, right? And it becomes smaller and smaller, and when it disappears, it means that it is equivalent or homeomorphic to the sphere. However, he noticed that sometimes you have some singularities. So when you apply the Ricci flow, sometimes the topology will have some sharp singularities edges. These are the singularities. Then Perelman could try to find a solution to say that, okay, we can have the surgery on these. So these are the concepts in algebraic topology. You can have surgery on these singletons, and they are also he proved that these are finite. So there are not infinite number of them. And then he could actually prove the Poincare conjecture. It's very interesting. He put his papers, 2 papers, on archive. He didn't publish them because he wanted this to be open access and everyone sees that. And I think he did a great job. I really support him in that way. Also, he didn't accept uh, uh, many awards such as Fields Medal for his own reasons. But yes, he was a great scientist who proved Poincare conjecture. So this was one of the most famous conjectures in algebraic topology that was proved. I think it was proved around in the decade of 2000 to 2010. So it took about 6 years for scientists to approve Perelman's proof, something like that. Okay, let's continue. This was a parenthesis for how algebraic topology is cool, especially the Ricci flow. Okay. So let me share screen and continue the lecture. Now let's talk about Riemannian manifold concepts. For Riemannian concepts, so we have tangent space, we have metric, and we have norm. Tangent space, Txm, what is it? It's the space of tangent vectors on the manifold M at point X. So it means that this is a manifold. Assume this is a manifold. Here, for the sake of visualization, is locally 2D. At every point, we can have a tangent space, or you can see it as a tangent hyperplane on the manifold, it is tangent on the manifold at that point. So we write it as Txm. So it is tangent on M, manifold M at point X, right? And as you see, this is, for example, locally 2D. This is the tangent space is also locally 2D. It's a 2D hyperplane. In general, when the manifold is locally d-dimensional, the tangent space is also locally d-dimensional, and that is a d-dimensional hyperplane. Okay, that's one thing. Riemannian metric G, so it's G zeta. It takes 2 tangent vectors, 2 vectors in the tangent space or tangent vectors, and it outputs a scalar. So zeta and eta here are 2 tangent vectors, and the tangent space is at point X. So these are 2 vectors in the tangent space at point X, right? This is the metric, and the metric simply calculates their inner product of these 2 tangent vectors. And of course, as we have in Euclidean space, we can define norm using the inner product, or here using the metric. So the square root of the metric of a vector and itself, you can see it as the norm of zeta at point X. Why? Because you can see norm as the square root of inner product of the vector with itself, right? Okay. Now, the length of the curve. Consider this is the curve C. I want to calculate its length. So I can divide it into several points, and I can have piecewise linear lines in order to approximate this length. So I can have the summation of these linear lengths, and this is approximately the length of this curve. The more points I have, the better approximation. N is the number of lines approximating it. So when you increase N, it is a better approximation. And so we can say the length of the curve X and T, for example, here T is 0, and at the end T is 1. So you can see T as a parameter of the curve. Is approximately summation of the lengths of each of these lines. So xt minus xt plus 1, something like that. So t goes from 0 to n. Consider these are the number of lines. This approximation becomes exact when you limit n to infinity, because this approximation becomes more accurate by increasing n. Then I can also multiply and divide this by delta t, so they can cancel each other. It's the same. And then I can use the Riemann's sum to convert limit of summation to integral. Do you remember what was Riemann's sum? For example, we want to calculate the integral under this curve. How do I do that? I can have several rectangles under it. And let's decrease the width of these rectangles, or in other words, increase the number of rectangles. Like here, we are increasing the number of lines, increase the number of rectangles. By limiting the number of rectangles to infinity, then this summation converges to the integral of this curve. This is exactly Riemann's sum. So here, integral, it becomes integral of this. And what is this? This is like the definition of derivative where delta t goes to 0. All right. So it's derivative of xt with respect to t, or denoted by this. And in general, when we go from point A to point B, we can replace this 0 and 1 with A and B. So you can see the length of the curve x with parameter t is the integral of normal derivative of x with respect to t dt. T goes from from A to B. So this is the length of the curvy line on the manifold. Okay. Now, geodesic, gradient, and Hessian. Geodesic, it is locally minimizing curves between 2 points on the manifold. Simply, it is the shortest curvy line connecting 2 points. Or locally minimizing, you're locally minimizing the curves between 2 points on the manifold. Okay. And Riemannian gradient is the direction of steepest descent of the cost function, or maximum growth of the cost function on the manifold. What was it? It is the generalization of Euclidean gradient to Riemannian space, Riemannian manifold. What was the Euclidean gradient? It was the direction of maximum growth of the cost function, the direction of derivative, right? Now it is Riemannian gradient is the direction of maximum growth of cost function on the manifold, rather than in the Euclidean space. So gradient denoted by this, you can write it as these two or this. Basically, it means this. And what is this, by the way? This theta is a vector in the tangent space. This is delta t is a curve, and this is the derivative of curve with respect to parameter t of the curve. We talked about t here in this slide. Also, you can denote it different notations. Okay, this is derivative of f of x along the direction zeta, tangent vector zeta. Okay, Riemannian Hessian is again an extension of Euclidean Hessian to Riemannian geometry. It's a derivative of one of the directions zeta in the tangent space. It can be seen as a derivative of derivative, so it's a second order derivative. You can see as this. Bf of x zeta equals partial gradient of f of x in the direction zeta. B denotes the Hessian matrix. It is interesting that in the pure optimization papers, they usually denote Hessian by B and inverse of Hessian by H. So H in pure optimization papers doesn't denote Hessian, but inverse of Hessian. B is Hessian, and partial Zeta is a affine connection. You can see affine connection as derivative of one of the directions in the tangent space that we have written here. Okay. Now Riemannian concepts, other concepts, logarithm and exponential maps. So we have logarithm map and exponential map. What is that? So in Euclidean space, we have subtraction, right? Like this. We have 2 points, xn and xm. We can subtract them and it gives us a vector connecting connecting xm to xn. We can generalize subtraction in Euclidean space to Riemannian geometry, and it gives us logarithm map. So logarithm map is the generalization of subtraction in the Riemannian geometry. What does it mean? It takes 2 points on the manifold. It gives a tangent vector in the tangent space. Like here, we have 2 points. It gives vector. It also takes 2 points on the manifold. It gives a vector, a tangent vector in the tangent space. And it's denoted by these, like this. So it gets 2 points, xn and xm. It gives the tangent vector delta, or let it be this. And this tangent vector zeta belongs to the tangent space of xm, not xn, xn. Okay. Now consider the addition in the Euclidean space. Xn equals xm plus delta. So it takes some point and some vector, and then we add them. It gives us a point. It gives us a point. Then it means that here xm is a point, delta is a vector, xn is a point. So I can generalize this addition to become exponential map in the Riemannian geometry. And what is that? So you get a point on the manifold M, a tangent vector in the tangent space like this. We have point vector, and it gives us a point on the manifold. We denote it by this exponential map of delta at the point xm. It gives us xn. Or this exponential map of zeta at point xm gives us xn, where zeta belongs to the tangent space of xm. Okay. So in simple words, logarithm map is the generalization of subtraction. Exponential map is the generalization of addition for the Riemannian geometry. Now, Riemannian, some other concepts, Riemannian concepts, is retraction. Another concept that we are going to talk about is retraction, and that is that, what is that? Exponential map, what does it mean? So we said that it means addition, is like a generalization of addition. And it means that assume this is a manifold. I want to move from this point to this point on the manifold in the direction of zeta. Zeta itself is a tangent vector in the tangent space of at point x, right? So if I move on the manifold like this, curvy, on the curvy manifold in the direction of zeta, like this is exponential map. And as you see, it's very hard. It's very curvy, so it needs differential geometry. So we can replace or approximate the exponential map by retraction. What is retraction? Retraction says that rather than going on the curvy manifold, go in the flat tangent space in the direction of zeta, and then project this point onto the manifold. So rather than going in this curvy direction, go straight and then project. This is retraction. Retraction is a mapping from the tangent space to a point on the manifold. It's denoted by this retraction of vector zeta at point x. It gets the point x on manifold, and the tangent vector in the tangent space, it gives a point on the manifold. We can see it as projection of the point, this point, in the tangent space onto the manifold. Okay, so this is retraction. Okay, another concept is parallel transport and also Riemannian curvature. Let's talk about them. What is parallel transport? It's moving or transport, move or transport a tangent vector on the manifold in a way that it stays parallel with respect to the connection. In simple words, let's visualize it. It means that, for example, come from here, you have these tangent vectors. So with respect to this curve, it remains parallel, as you see, and then it becomes like this, you come back to here. So there is some angle from this and between this and this. So when you start from a point, you go on the manifold in some direction and come back to where you were. If you have curvature on the manifold along that curve, along that path that you move, you will have some angle. So if consider the flat Euclidean space, if I move on this path in this Euclidean space like this, I have this. Let me draw it. So I will have something like this. As it is flat, these are parallel to each other, parallel transport. And at the end, where I will match exactly where I started. And the angle between these two is 0. The angle is 0. Why do they stay the same, parallel the same? Because it's flat. But these are not staying the same in parallel to each other because there is a curvature here. It's curvy, okay? And this alpha shows the amount of curvature. So it's an indication of curvature, actually. The more curvature we have, the more angle we will have. 0 angle means that there is no curvature in this path on this manifold. So this is the concept that Riemann found out, and it's called Riemannian curvature. So assume we do parallel transport on a tangent vector on the manifold and return back to the starting point. If the starting and ending tangent vectors do not match exactly, it means that the manifold has curvature. This is the idea of Riemannian curvature. Okay. Now let's talk about vector transport. Parallel transport, which I talked about, is hard to compute. It needs differential geometry. We can approximate or replace parallel transport by vector transport. Do you remember? Exponential map was hard to compute, needed differential geometry. We replaced or approximated that by retraction. Parallel transport is hard to compute. Let's replace or approximate it with vector transport. Okay. Vector transport is a mapping from a tangent space to another tangent space on the manifold. So it's denoted by this tx1, x2, zeta. So we are mapping a tangent vector to another tangent vector in another tangent space from x1 to x2. And these are 2 points on the manifold. Zeta belongs to tangent space of x1. The output of the vector transport belongs to the tangent space of x2. You can see it as this. So you have some vector zeta in this tangent space. I want to go from point x to y here. Y also has its own tangent space. What is this tangent vector in the tangent space of y? What is the corresponding vector to this zeta in this tangent space? That would be the vector transport. So if you vector transport zeta from x to y, you will get this, because its correspondence is this, right? This is called tangent. So you can use this vector transport to approximate parallel transport. I think if you also take a look at this, you will see that it's kind of having a vector transport. This parallel transport can be seen as vector transport. So this vector is in this tangent space. This vector is also in this tangent space, right? Okay. So you can see it as moving a tangent vector in a tangent space to the corresponding tangent vector in another tangent space. Now we have talked about the concepts. Let's start briefly talking about Riemannian optimization. So whatever we had Euclidean optimization, we usually had first order or second order Euclidean optimization. We can extend those, generalize those to have first order and second order Riemannian optimization. Simply because Euclidean space is a special case of Riemannian space, right? Riemannian geometry. Okay. Riemannian stochastic gradient descent. A stochastic gradient descent, or gradient descent. They have called it the stochastic gradient descent, but I think what they are doing here is gradient descent. A stochastic gradient descent means that you have several points, you take randomly one of them in each iteration, but doesn't matter. The concept is important. Gradient descent in Euclidean space is this, right? Every point, update of every point is xk minus lambda gradient of f of xk, right? So you move, your update is this. This is your update. Minus lambda. Lambda is the learning rate, and k is the iteration index here. You can also bring this to the other side to restate it in this way. But let's take a look at this. What does this mean? It's actually meaning xk plus minus lambda gradient of f of xk. All right. Now recall this slide. We said the generalization of addition in the Riemannian space is exponential map, right? Here we also have addition. So this plus this. We can write it in this way, in Riemannian space. So xk, point xk, and this is the direction, this is a vector in the tangent space, minus lambda gradient of f of xk, right? In the tangent space of xk. So this simply means xk plus, you can imagine it as plus, minus lambda gradient of f of xk. And this is the left-hand side, the same. So this can be generalized to be like this in the Riemannian space. It gives us the update in each iteration of gradient descent or stochastic gradient descent in Riemannian space. It was proposed in 2013 in paper 7. Okay. This is addition, sorry. Where addition in Euclidean space is generalized to the exponential map in Riemannian space. Okay. For simplicity, we can, but as we talked about this in this slide, exponential map is hard to compute. We can replace it by retraction. So we can replace this exponential map by retraction to be simpler. Both work for Riemannian gradient descent. This was an example. We can have other Riemannian first order optimization methods. This was an example. Now let's talk briefly about second order Riemannian optimization, such as this Riemannian Newton's method. So we know that in iterative optimization algorithms are like this. Xk plus 1 is xk plus some delta x, some update, right? And delta x in gradient descent is minus lambda gradient of f, right? Here, in Newton's method, it uses Hessian in updating this step. It uses both Hessian and gradient. And delta x is this, minus Hessian inverse gradient. For proof of this, take a look at my lecture in optimization techniques. In one of the lectures in my YouTube channel, I have talked about Newton's method. So you have this. You can also left multiply the sides by Hessian. So Hessian and Hessian inverse cancel each other. We can restate this equation 10 as equation 11. Doesn't matter. Okay. Now we can generalize this equation 11 to have a Riemannian Newton's method. Recall Riemannian Hessian. We had it here. Do you remember? Here in this slide. I'm repeating it here. Interestingly, they're very similar. If you compare, this is Newton's update in the Euclidean space, and this is Riemannian Hessian. So this is Riemannian Hessian, right? B. And here also, this is Hessian. This is Euclidean Hessian. Delta x is the update. This is zeta, is the update, the tangent vector. And this is the gradient. Okay. So Riemannian Newton's method, if you compare this equation 11 and this, you will get this. So you have b f of x, zeta equals minus gradient of f of x. So this is Riemannian Newton's method for unconstrained second order optimization. If we have constraint optimization problem, we need to use interior point method algorithm, which also uses Newton's method in it. You can take a look at my lectures for interior point method on my YouTube channel. Also, we can have quasi-Newton's methods. Quasi-Newton's methods try to approximate the Hessian, because Hessian is usually hard to compute. So we can approximate either the Hessian or inverse of Hessian for the Newton's method. And one of the famous quasi-Newton's methods is BFGS. Quasi-Newton's methods, including BFGS, approximate the inverse Hessian matrix by dense matrix D by D. For large D, storing this matrix is very memory consuming. So in 1980s, limited memory BFGS or LBFGS was proposed by Nocedal et al., which uses much less memory than BFGS, because at that time computers were developing and memory was very important. I have talked about LBFGS and BFGS briefly in my lectures on YouTube, so you can take a look at them. But if I want to briefly mention them here, LBFGS algorithm can be implemented as shown in the following. This is the implementation which is inspired by the algorithm in Nocedal's book, chapter 6, Nocedal and Wright's book. As Nocedal has proposed LBFGS, he's very expert in this area, so he has explained BFGS, LBFGS, and all of these quasi-Newton's methods in chapter 6 of his book. So here, in simple words, I can say that I have briefly mentioned in that lecture video in my YouTube channel, but I can say that we have a recursive function for LBFGS up to maybe 10 previous history. So we have 10 folding of the Hessian, and as we don't go in the stack of the recursion a lot, we only go for 10 previous memory in the stack. We don't use a huge stack. If we use a huge stack, then it will use a lot of memory. It won't be limited memory anymore. But as we are using a small amount of a stack, it's not using a huge memory in the recursion in the computer, and therefore it's not an issue for the memory. But why is it limited memory? Because it's approximating the inverse of Hessian by a scalar times identity matrix. So it's diagonal matrix and it's a scalar times identity matrix. It means that it's approximating the whole Hessian by a scalar. And it updates it using some recursion like this. Okay. This is LBFGS. I have repeated it here too. This is Euclidean LBFGS in 1980s to 1989 by these papers 8 and 9 by Nocedal. Okay, you can and Riemannian LBFGS extended this Euclidean LBFGS to Riemannian geometry. It was proposed in 2020. You can see it as an extension in paper 10. And what does it do? It says that I have, for example, let's compare this. So compare line 6 here. Xk plus 1 equals xk minus eta pk. So this is replaced by retraction or exponential map, as we talked about it here, right? Also, we have, by the way, as from going from one point to another point, the space is changing. The space of the tangent vector is changing. So we need to have, like here, we need to have vector transport from xt to xt plus 1, from one of the x in this iteration to the x in the next iteration. Otherwise, the two vectors are in different spaces and we can't do any arithmetic on them. So we need to have vector transport from one space to another space in the Riemannian LBFGS. But in Euclidean LBFGS, we don't have these issues because all of the vectors are in the same space, even in different points, right? We have only one Euclidean space. But in the Riemannian geometry, we have, and at each point, we have a separate tangent space. That's another thing which you should note. We also have here the vector transports, also the adjoint vector transport. You can see the adjoint vector transport like the inverse of vector transport. Although it's not mathematically completely correct, it's not exactly the inverse, but you can imagine it to be like the inverse. So going from this point to this point is the vector transport. Going back from this, the tangent space of this point to this point is called, you can see it as adjoint vector transport, although it's not completely correct mathematically to say that. Okay. And important Riemannian matrix manifolds. So one of them is Stiefel manifold, denoted by ST, P, and D. What is it? It's defined as the set of orthogonal matrices, like this. So M, denoted by ST, P, and D. Stiefel was a scientist, by the way. ST, P, and D, it means that the set of matrices of dimension D by times P, so with D rows and P columns, where X transpose X equals identity matrix. It means that where X, the matrices X are orthogonal matrices, or their columns are orthonormal. And as they are D by P, we denoted by ST, P, and D. So we have P columns, each of which is D-dimensional. And each of these P columns has the length 1 unit length, and also the inner product of these D-dimensional columns with each other is 0. So they are perpendicular to each other, orthogonal to each other. The quotient of a vector space V by a subspace N is a vector space obtained by collapsing N to 0. So it's a subspace N, but you collapse that to 0. So you will have the rest of them. So whatever is the rest of the space, excluding the subspace N, is the quotient, right? The obtained space is called the quotient space, and it is denoted by V/N, and it is read as V mod N or V by N. Okay. So for defining Grassmannian manifold, we need quotient manifold and Stiefel manifold. Grassmannian manifold or Grassmann manifold, denoted by G, P, and D, can be seen as the quotient space of the Stiefel manifold ST, P, and D. Reference 1. You can see it as this. So manifold, Grassmannian manifold is Stiefel manifold PD mod Stiefel manifold PP. The Grassmannian manifold G, P, and D is a space of all p-dimensional linear subspaces of the d-dimensional vector space. So every element of this manifold can be the linear column space of the projection matrix X from a d-dimensional into a space of p-dimensional subspace where p is less than or equal to d. So let me explain this in detail. What do I mean? Consider the projection matrix X, X transpose A. What does it do? X transpose A projects the columns of A onto the column space of X. So it's a linear projection. So assume A has some columns. Okay. And X also has some columns. X itself has some columns. We can form a space by linear combination of these columns. In other words, that space is spanned by the columns of X. And if the number of columns is less than the number of rows in X, yes, that column space would be a subspace because P is less than or equal to D. So X is D by P. If P is less than or equal to D, it means that we are reducing the dimensionality of A. So we are projecting it onto a subspace, okay, a p-dimensional subspace. So from d-dimensional input, each column of A is d-dimensional. So because X is D by P, so X transpose is P by D and A is D by N, for example. So you are projecting each d-dimensional column in A onto a p-dimensional column space of X. Then these projection matrices in linear projection, the set of all of them is a Grassmannian manifold. So Grassmannian manifold is closer related to linear projection for projection matrices onto this column space or onto the subspace. Okay. Okay, now Grassmannian manifold can be seen for linear projection, as I said. In many machine learning methods, it has been used also, such as PCA, FDA. You can see them as Grassmannian manifolds because they have linear projection on them. Also, every layer of neural network before the nonlinear activation function is a linear projection, right? You can see the weight matrix as a linear projection matrix. So you can see every layer of neural networks as a Grassmannian manifold before the activation function. Symmetric positive definite manifold or SPD manifold. We denote it by S++. S plus means X belongs to positive semi-definite cone. It means that its eigenvalues are either 0 or positive. They are non-negative. But S++ means X is positive definite. Its eigenvalues are positive, neither negative nor 0. Right? So SPD manifold X is symmetric and it's also positive definite. And so it's symmetric and positive definite. All of its eigenvalues are positive, neither negative nor 0. We have a lot of examples of this in real world in science, such as covariance matrix. It's a positive definite matrix. Or the weight matrix in quadratic functions, such as X transpose W, X, Y. Because if W is positive definite, this quadratic function is facing up, so it's convex. If W is negative definite, it's facing down, it's concave. So for this to be able to minimize, we need W to be positive definite. For this if we want to maximize this, W needs to be negative definite. Because we can minimize this or we can maximize this, right? The weight matrix in the generalized Mahalanobis distance This is generalized Mahalanobis distance, W. This is the weight matrix. If you set W to I, this becomes the Euclidean distance, a squared Euclidean distance, right? So what does it mean? You can see this. It can be proved that you can see generalized Mahalanobis distance as first have a linear projection onto a subspace and then apply Euclidean distance in that subspace, okay? This projection matrix needs to be positive definite or positive semi-definite. Why? To be both convex, so because we want the distance to be convex, and also to satisfy triangle inequality, to be a valid distance metric. Otherwise, it's not a distance metric. It needs to be positive definite to satisfy triangle inequality. Okay. There are some toolboxes, papers, and references. Let's look at them. Important toolboxes for Riemannian optimization. One of them is ManOpt in MATLAB. So ManOpt, short for manifold optimization. It's the most famous optimization toolbox for Riemannian optimization. The other one is PyManOpt, the Python version of ManOpt. Yeah, these are the websites of these toolboxes. The other one is Stockman. It's in Python. It's for stochastic manifolds, or noisy manifolds. The other one is geomstats, short for geometric statistics, maybe. This is in Python and mostly for machine learning, Riemannian optimization for machine learning. The other one is GeoOpt, short for geometric optimization. It is in PyTorch. PyTorch itself is in Python for deep learning. The other one is Raptlib. It is in C++. This is the ManOpt version in C++. So PyManOpt is ManOpt version in Python. Raptlib is the ManOpt version in C++. The other one is Mixtest. It's in MATLAB. It has implemented Riemannian LBFGS and also mixture models using Riemannian optimization. Okay. Now, some important papers and books in this area. First off, there is a page in Papers and Codes. It's a Papers with Codes. It's a website which lists many of the papers, categorizes them, and it shows their GitHub pages too, right? They didn't have any page for Riemannian optimization. I actually made that for them. And I added some of the Riemannian optimization papers to that. And then afterwards, many Riemannian papers were automatically added to that category. And they also gave me, because of these contributions, they gave me their first contribution award. And I have their award in my house. It's interesting. Also, the books of John M. Lee on topology and manifolds. So there are two important books: Introduction to Topological Manifolds and Introduction to Smooth Manifolds. First, you need to read topological manifolds and then smooth manifolds, because the smooth manifolds are topological manifolds with some additional characteristics that we discussed in the slides. These are two important books published by Springer. Two very good books on Riemannian optimization. Optimization algorithms on matrix manifolds by Apsil or Pierre Anthony Apsil, reference 1. This is the most important book in the field of Riemannian optimization. The other one is An Introduction to Optimization on Smooth Manifolds by Nicolas Baumol, reference 2. This is also a very important book, which is more recent in Riemannian optimization. Some important papers. A Brief Introduction to Manifold Optimization. You can see it as a survey in 2020. Riemannian BFGS or RBFGS. It was proposed in 2010. Proving convergence of RBFGS in 2012 and 2015 in these references. Analyzing the properties of RBFGS in 2013. Also, as vector transport is computationally expensive in RBFGS, it's very hard to compute. Cautious RBFGS was proposed in 2016, which ignores the curvature condition in the Wolfe conditions. Wolfe conditions proposed in 1969 are two conditions for line search in second-order optimization. For Armio condition and curvature condition. Armio condition itself is used in backtracking line search, also used in first-order optimization. Curvature condition makes sure that the approximation of Hessian in the Quasi-Newton's methods remains positive definite, because Hessian by definition is positive definite. Okay. Then they said, okay, the curvature condition requires vector transport. So they said, let's get rid of the second condition, Wolfe conditions, and only consider the Armio condition proposed in 1966. But how do we make sure that the approximation of Hessian is positive definite? Let's check a cautious condition proposed in 2001 before updating the approximation of Hessian in the Quasi-Newton's method. Because BFGS is a Quasi-Newton's method, right? The cautious RBFGS has been used in MANOPT toolbox nowadays in 2000. So MANOPT was proposed in 2014. Cautious RBFGS was proposed in 2016. When it was proposed in 2016, they updated the MANOPT toolbox to have cautious RBFGS. Nowadays, it has cautious RBFGS. RLBFGS and SPD manifolds, you can see them in paper in these papers in 2015, 16, and 2020. Mostly they are talked about by Professor Subrat and Professor Reshat Hosseini. Some other extensions of Euclidean BFGS to Riemannian spaces. There is a thesis in 2007 in a university in Australia, which also talks about some direct extensions of Euclidean BFGS to Riemannian BFGS. See the reference 30, chapter 7. Also, vector transport free Riemannian LBFGS in 2021. This is our own paper. I wrote this paper. We proposed this method with my friend Reza Godaz and also with Professor Reshat Hosseini at the University of Tehran and some other co-authors. So what is this paper? It says that we know in RLBFGS we have a lot of vector transports, right? But they are very computationally expensive and time consuming. So let's find some mapping in the tangent space in a way that the vector transport operator becomes identity map. So you don't need to do anything. And also, interestingly, by our mapping in the tangent space, one of which was Cholesky decomposition, by our mappings, in addition to making the vector transport identity map, we also made the inner product or the metric G similar to the inner product in the Euclidean space. So we killed two birds with one stone. We made the vector transport identity, and we made the inner the metric like the Euclidean inner product. Okay. Also, some important scientists and scholars in the field of Riemannian optimization, some of which are here. There are many of them. Some of them are here. Absil, Pierre-Antoine Absil in UC Louvain in Belgium. Many of them are actually in Belgium. It is author of book 1. The most important scholar in this field is Absil. Book 1 is the most important book in the Riemannian optimization. He also is proposer of MANOPT toolbox. Rodolphe Sepulchre in KU Leuven in Belgium, co-author of Absil in book 1. Robert Mahoney in Australian National University, Australia. In Australia also, some people are doing it. Co-author of Absil in book 1. Nicolas Baumol, he is in EPFL in Switzerland. Author of book 2, the second best book in the field of Riemannian optimization. He is also the co-author of AppSil in ManOp Toolbox. Silver Bonnebel in Minas Paris PSL in France. He proposed Riemannian stochastic gradient descent. Do you remember? We have gradient descent, Euclidean gradient descent. He extended that to Riemannian gradient descent. Ring Wolfgang in Karl Franzen's Universität Graz in Austria. Many people in Europe are doing that, like this. He has the proof of convergence of RBFGS. Bart van der Dreyken in University of Geneva in Switzerland, again in Europe. Proposer of low-rank matrix completion by Riemannian optimization. Professor Suvritsra in MIT, USA. He is very good in optimization, also Riemannian optimization. Professor Reshat Hosseini in University of Tehran, Iran. He has proposed mixed toolbox. Also, he has worked a lot in SPD manifolds and mixture models using Riemannian optimization. Reshat Hosseini and Suvritsra collaborate a lot. Mertash Harandi in Monash University in Australia. He proposes a lot of machine learning algorithms and signal processing algorithms using Riemannian optimization. Soren Hauberg in Technical University of Denmark in Denmark. He has proposed the Stockman toolbox. You remember? It was for stochastic manifolds or noisy manifolds. Also, he has used machine learning using Riemannian optimization. I also thank my friend Reza Godaz, see our paper together, who introduced the field of Riemannian optimization to me. I also thank Professor Reshat Hosseini, who helped me understand this field too. Some acknowledgements. The slides of this slide deck are inspired by the teachings of Professor Reshat Hosseini at the University of Tehran. He also gave a virtual talk about Riemannian optimization entitled Manifold Optimization in Data Analytics at the Sharif Optimization and Application Laboratory in Department of Mathematics at Sharif University of Technology in Iran. And some slides of this slide deck are also inspired by the presentation of Professor Soren Hauberg at the ACML, Asian Conference on Machine Learning in 2021, entitled Differential Geometry in Generative Modeling. How do I know this talk? Because we were presenting our paper, Vector Transport Free Riemannian LBFGS in ACML 2021. Me and Reza Godaz. Also, one of the co-authors was Professor Reshat Hosseini in that paper. When we were presenting that, one of the talks was by Professor Soren Hauberg in this area. I talked that especially the things which are about extensional subtraction and addition to become logarithm map and exponential map respectively, and also the curvature of the length. These I took these. I was inspired for these things. I was inspired by his lecture, the lecture of Professor Soren Hauberg. Some of the concepts on topology and smooth manifolds. In this lecture, the ones which I talked about, topology, smooth manifolds, and these things in differential geometry and algebraic topology, in this lecture are inspired by the teachings of Professor Spiro Karigianis at the Department of Pure Mathematics in the University of Waterloo. His course, Smooth Manifolds. He kindly let me sit in his course, Smooth Manifolds, and I learned a lot from him. I thank my friend Reza Godaz and Professor Reshat Hosseini. See our paper together on vector transport free Riemannian LBFGS, who introduced this field to me. Also, our tutorial on optimization has briefly introduced what Riemannian optimization is. Some references, important references in this area. Okay, so one of them is, this is the most important book in the field of Riemannian optimization by AppSil et al., published in Princeton University Press. Optimization algorithms on matrix manifolds. The second best book in this field, which is more recent, is by Bumol, An Introduction to Optimization on Smooth Manifolds. In 2020, it wasn't yet published. We could find it in his homepage. I don't know whether it has been published now or not. This book, Introduction to Topological Manifolds by J. Lee, also another book of him, Introduction to Smooth Manifolds, both published by Springer in 2010 and 2013. First read this and then this, because you need to understand topological manifold to then understand a smooth manifold. Then General Topology. This is also a book in 2017 by Kelly. This is the paper Low-Rank Tensor Completion by Riemannian Optimization. Also, this is the paper of stochastic gradient descent in Riemannian manifolds. Do you remember? Riemannian gradient descent is this paper proposed in 2013. What is this? So this is Nocedal, 1980s. These and these papers together, they are proposing in 1980 and 1989 by Nocedal et al. Proposing limited memory BFGS or LBFGS, updating quasi-Newton matrices with limited storage on the limited memory BFGS method for large-scale optimization. These are LBFGS algorithms in Euclidean space. Okay, this one. The paper of Professor Reshat Hosseini and Professor Suvrit, an alternative to EM for Gaussian mixture models, batch and stochastic Riemannian optimization. What is this? This paper has extended Euclidean LBFGS to Riemannian LBFGS. Also, they have proposed some method to solve Gaussian mixture model without expectation maximization using Riemannian optimization. This is the book of Nocedal and Wright's Numerical Optimization, a very important book in Euclidean optimization. Chapter 6 of this book talks about Quasi-Newton's methods, such as BFGS and LBFGS. This is a Manopt toolbox by Bumol and Apsil and Spelcher, these people, and Mishra. This is PyManopt toolbox, Python version of Manopt in 2016. This is a Stockman toolbox in 2021. This is Geomstats toolbox in 2020. This is GeoOpt toolbox in 2020. This is Raptlib toolbox, which is Manopt toolbox in C++ in 2017. And as you see, Apsil is also a co-author here. By Reshat Hosseini and Mash'al, Mixest. What is this? It's an estimation toolbox for mixture models, but it uses Riemannian LBFGS. It has implemented Riemannian LBFGS too. This is a brief introduction to manifold optimization, a kind of a survey or introduction to this area. This is Riemannian LBFGS algorithm with applications. This is also a good paper in 2010 by Apsil. Let me remember this. Yes, so yeah, 24, okay. So 24, this paper, this is the paper of cautious RBFGS, which is all in 2016, which is also used nowadays in Manopt. I talked about it briefly. 21, this is optimization methods on Riemannian manifolds and their application to the shape space, published in SAM Journal on Optimization, which is a very good journal in optimization. This is a very important paper proving the convergence of RBFGS, Riemannian BFGS algorithm. Also, a Breudian class of quasi-Newton methods for Riemannian optimization. This is also talking about the convergence of Riemannian BFGS. Both of these talk about that. This talks about the properties of the BFGS algorithm, Riemannian BFGS algorithm in 2013. Again, 24 is cautious RBFGS. This is the paper of Wolfe for Wolfe conditions in 1969. Paper of Armillo in 1966 for Armillo condition used in line search, in backtracking line search. These global and the global convergence of BFGS method for so this talks about the convergence proof of BFGS algorithm, 2001. Zubrit-Sra and Reshat Hosseini, conic geometric optimization on manifold of positive definite matrices. So it talks about Riemannian optimization for SPD manifolds in 2015. Again, a paper by them in 2016 talks about, especially these two papers talk about Riemannian optimization on SPD manifolds. This is optimization approaches on smooth manifolds. The thesis that I mentioned, which has also kind of proposed a direct extension of Euclidean BFGS to Riemannian BFGS. Chapter 7 of this, I guess, as far as I remember. Here, yes, I mentioned that. So it's a direct extension of Euclidean BFGS to Riemannian spaces. Chapter 7 of this thesis in Australian National University. This is our paper. Co-authors, two of the co-authors are Reza Godaz and Reshat Hosseini. So we have proposed vector transport-free Riemannian LBFGS for optimization on symmetric positive definite matrix manifolds in ACML 2021. This is low rank matrix completion by Riemannian optimization in 2013, and this is our tutorial paper, my tutorial paper on optimization. Okay, I hope this has been useful for you. Thank you.